Hello, I'm JW. This time I'm going to have a look at voltage drop and in particular how it relates to energy wastage or energy efficiency within an electrical installation. Now this might not be something you've actually thought of, but if you think about a typical cable for a circuit, it has a certain amount of resistance in it, and if you pass a current through resistance then some power is going to be given off as heat. So cables do of course get warm in operation, and in some cases they can get quite hot. I understand a PVC cable is rated to around 70 degrees centigrade, so if it was running at its full operating current, it is going to get pretty hot there. And of course that heat being given off by the cable is effectively waste, because it's not obviously powering the load at the end of the cable, it's just being dissipated into the environment and basically thrown away. Now in a lot of cases that particular amount of heat is incredibly small, and so small in fact that it's really insignificant in the scheme of things. However, there are certain circumstances where it most definitely is not insignificant, and it may be appropriate to use a larger sized cable just to avoid the fact of the amount of losses you're going to get, because of course bigger cable is going to have a much lower resistance, therefore less heat is going to be given off and less heat is wasted. So we'll have a look at a couple of examples and how you can actually calculate that and see if it does actually make any kind of difference on a real circuit. Now, in order to calculate the losses in a conductor, we need two things. First of all, we need to know the current flowing in that conductor, and that would generally be the design current for the particular circuit. So in other words, whatever's connected at the end of it, how much current is going to be used there. And then the second thing is the resistance of those conductors. Now, you can find the resistance of conductors in a couple of places, one of which is in the on-site guide. Here's the blue one that's currently in use in 2020, and then the other place you can find it is in Guidance Note 3. Again, this is the one with the blue on the bottom, the current edition, and in theory you can get them from manufacturers of cables and whatever else if you happen to want to go and be bothered with that, but this will do perfectly fine. In this particular book it's in Appendix B, so we'll have a look in the back there, and all this is just a list of various sizes of conductors and then the resistance of those particular conductors, whether it's copper or aluminium. Copper usually, that's what we're going to be using for this example. Now this table in the on-site guide is exactly the same, the only difference is it's printed in smaller text because it has smaller pages, but we'll use this one because it's a bit bigger, easier to see obviously. So values of resistance per metre for copper and aluminium conductors, and of R1 plus R2 per metre at 20 degrees Celsius in milliamps per metre. So various sizes of conductors listed down here. Now the reason it's given you the two types here is so that first you can just get the resistance of one of the conductors, and also if the line conductor and the protective conductor combined, that's when you would do that R1, R2 test where you link the line and protective conductor at the consumer unit and then test at the end of the circuit or at each point to ascertain what the resistance is. And you can actually use these to give you an idea of how long the circuit is. So if you say had a lighting circuit with say 1mm square conductors, if you did an R1, R2 test and it came out to say 362 milliohms, then that would indicate it was approximately 10 metres long, because that's 10 times the value here, this value being for 1 metre length. And the main thing to note here is that the values obviously are different, because where it's just got 2.5 and then nothing, that is literally just measuring the value of a single length of conductor. Could be the line conductor, but in fact it could be any piece of copper conductor, line, neutral, whatever else, it doesn't matter, it's just the material itself. 2.5 and 1 is those two of the same length combined in series, so that would be like your old twin and earth where it had the 1mm squared protective conductor. 2.5 and 1.5 is sort of modern twin and earth with the 1.5mm square conductor, and then where both values are the same, that's the sort of thing you'd use where you had say conduit wiring, so you obviously pulled in both those conductors and they were of the same size. Now calculations for this can get a bit involved, particularly if you've got a circuit with multiple points along its length, because then you've got different voltage drops along the length depending on what the load is. So for this particular example, we'll consider this as a fairly simple example. So we're going to have our consumer unit here, somewhere in the house there. We're going to have our conductors, which go along to an end point, and then on the end point here we're going to have some kind of load. And for this particular example, we're going to call this an electric vehicle charging point. And the reason we're choosing this is because an electric vehicle charger is going to be on for an extended time, typically many hours at a time, and it's also going to be of a decent loading, typically in range of either 3.5 or 7 kilowatts. And though you could do this for any circuit in the house, the reality is that for most domestic circuits at least, this isn't particularly significant because most circuits in a typical house are either very low loaded, things like lighting, particularly with LEDs and whatever, or they're only on for a very short time. So this could be an electric shower, but of course you don't generally stand in an electric shower for 6 hours at a time. It's only on normally for a few minutes. So although these principles apply pretty much to any circuit, it's only really significant when you've got a circuit that's fully loaded to a decent level, and it's also going to be loaded up for a decent amount of time, typically several hours. Now for this one, we'll say it's a 32 amp circuit, fairly typical choice there, and that would give us sort of a loading there in the region of around 7 kilowatts or 7.5 kilowatts or so. And to make the calculations a bit more obvious and easy, we're going to say that the length of the circuit is 10 metres. 10 metres, of course, is reasonably typical for a sort of thing like this, from the consumer unit through the house and outside to the charging point. We'll also say that the actual total load on the circuit is going to be the full 32 amps. That would actually be a load of 7.36 kilowatts in the case of 230 volts. But the voltage isn't particularly relevant here because all we need really is the current and then the resistance of that conductor. Now for the 32 amp circuit, we've seen in a previous video, which was about cooker circuits mainly, that there's a couple of choices you can use here for the size of conductor. If it's going to be surface clipped, basically just attached to the surface of a building, which is typically what you'd have in this sort of situation, or if it's going to be concealed directly in the masonry, sort of under plaster or whatever, then you can actually use 4mm squared conductors, and certainly if it's only run on for a short time, that is still a valid choice. However, in this case it's going along for a long period, so that may not be the best option. Next size up of cabling is 6mm squared, which again is what would normally be used for the cooker circuits of old on the 30 amp fuses, but so you don't necessarily have to use that now. And if you want to go above that, then the next size up is 10mm squared, and of course there are sizes above that, but then you're getting into rather silly territory because then it's getting ridiculously difficult to even fit them into the terminals of the equipment at the end. Now in terms of our resistance of conductors, we can look in our table here, which we saw previously, and again we just get the values straight from in here. Now it's important to realise we're not looking for the line and protective conductor because of course in normal operation the current is going to flow through the line, and the neutral conductors, it is not going to be flowing in that protective conductor. That's only put there for that particular test, and also for things like fault conditions and whatever else if you wanted to calculate them. So if we look down the table here, we want to have a situation where we want the resistance for the line and the neutral conductor. So that's going to be where these are both the same. So for 4mm squared there, we've got 4 and 4. That gives us a value there of 9.22. And essentially all that is just two lots of 4 in the series. So if you look at the 4 value there, it's 4.61. And if you multiply 4.61 by 2, well, guess what? You get 9.22 as well. So that's just for a single one. That's just for two identical conductors. So those are the values we want to use. So we could just get that twice, but I say it's exactly the same as printed there. So you can think that as line and the neutral. Of course, they're both the same size. So 4mm square conductors, resistance is 9.22 milliohms per metre. So we'll put that down here, 9.22. And then for the other values, 6mm squared, same thing again, just 6 and 6 there. We can see that value is 6.16. And for 10, it will be again the 10 and the 10, which again is 3.66. So just put those values on the form we had previously. And remember, those are in milliohms per metre of length of conductor. Now in this particular case, we have 10 metres of length of conductor, so we need to multiply these by 10. So we'll just quickly do that here. So it's going to be 92.2 milliohms, 61.6 milliohms, and 36.6 milliohms. And again, that's just multiplying those by 10. It gives you obviously 10 times greater. If this was 17 metres, we would just multiply it by 17. And if it was 300 metres, we would multiply it by 300. And if it was 300 metres, it would be totally non-compliant because the voltage drop would be huge and the thing on the end probably wouldn't even work. But nevertheless, that's the principle we're talking about. Now in terms of how much voltage drop we've got across here, there's two formulas we can use, and we've seen these in previous videos as well. One of which is the one that's usually called Ohm's law, which means that voltage is equal to current times resistance. And you can do this with voltage divided by current is resistance and so on. And then the other one is power in watts is equal to current times the voltage. Now we actually need both of these here because we've got two things we know, one of which is the current, which we know is 32 amps, and then the resistance is whatever it is of these, depending on conductor size. So you can actually rearrange these to get the information we want, and there is like a wheel-shaped thing you can use to get that a bit more quickly if you want. But the upshot of all of that is that the value we're really looking for here is power, because we want to see how much power is wasted in this conductor. We could calculate the voltage first and then put it into the other one here and all of that, but it turns out that power is equivalent to I squared times R, so the current times the resistance, and that will give us a result in watts of power basically wasted in the conductor. So how much power are we going to waste away? Now let's do it for the 4mm conductor first. So all we're looking for is the current times itself multiplied by the resistance. Now the current is going to be the same in all three of these, and that is actually 32 amps. So 32 multiplied by 32 gives a value of 1024. Fairly decent figure there. And then we've got our resistance here, so it's going to be 1024 multiplied by the resistance for whatever cable size we've got. Now important to realise these are in milliohms, which is basically 1/1000th of an ohm. So we need to actually account for the fact here, because if we use those as is, we're going to have a figure that's 1,000 times too big. So it's going to be this divided by 1,000 multiplied by 1024. So bear in mind the 32 is the I squared bit, and then we just multiply by the resistance at the end, but say dividing by 1,000 because these are in milliohms, they're not actually in ohms directly. So for the 4mm cable, it's going to be 1024 multiplied by our 92.2, and then we're going to divide all of that by 1000, and that will give us our power output in watts just from the cable itself. So that's basically going to be our wastage. So for that particular example, the answer is 94 point something, so 94 watts. And looking another way, as it's over 10 meters, that's about 9 watts per meter. That cable is going to get pretty warm in that case. Now, for the other one, it's the same thing, except it's going to be 1024 multiplied by 61.6 divided by 1000. So that's for our 4mm, for the 6, and for the 10. And the results we get for this one are 63 watts and some odd decimal places. And for the larger size cable, it's actually 37, and again 0.4 something or other as well, which we won't particularly go into with that. Now you can see there's quite a difference here between the largest and smallest, 94 watts, 63 watts and 37 watts, and of course that's being dissipated from the cable across its length, so it's about 9 watts a metre, 6 watts per metre, and just under 4 watts per metre if we use the biggest size. Now of course this is only in watts, we're not talking about huge amounts of power here, but nevertheless there is quite a difference between the highest and the lowest information. So how much would that actually cost over a typical year? And this is really why we've chosen an EV charger as the example here, because this doesn't really work with things that are only on occasionally. Now I've got a fairly typical electric vehicle. To charge it fully from almost empty to pretty much full is typically going to be in the region of sort of 8 to 10 hours on a 7 odd kilowatt charger. Now of course in most cases people aren't necessarily going to have it completely empty unless they drive sort of a couple of hundred miles every single day. So what we'll assume then is it's on for say 5 hours a day, and throughout the week we're not going to necessarily charge it up every single day. Maybe they only go out to work or something on the Monday to Friday or something. So we're going to say 5 days each week. 5 days a week, we'll say there's 50 weeks a year just to make it an easy calculation, so 250 days, which is 50 weeks times 5, and it's going to be 5 hours per day, so the total number of hours per year is those two multiplied together. 5 times 250 days equals 1,250 hours of charging use. And again, we'll assume that it's going to be at the full 32 amps, although in reality it could obviously reduce that depending on the type of charger you've got and various other factors. But again, just to make it simple there, so 5 hours charging each day, 5 days of the week, 50 weeks a year. They go on holiday for the other 2 and don't use the car. So 5 times 250, 1250 hours per year of current being used. Now, what about those figures we had previously? So we had those three figures there, so 94, 63 and 37 watts, depending on the size of cable that we chose for the installation, 4, 6 or 10 millimeters squared. And bearing in mind all of these would actually be valid choices, even the 4 millimeter, assuming it was on the surface or within plaster and whatever else. So our 4 millimeter square cable, we saw that was 94 watts. Now we need to know what the total usage would be over the year. Now, electricity is sold in kilowatt hours, and a kilowatt hour is 1 kilowatt electricity switched on for 1 hour. Now we already have the watts and we have the hours, so it's fairly straightforward to get these together. Now bearing in mind this is watts, not kilowatts, so to convert this to kilowatts we need to divide by 1000. So that gives us it in actual instead of watts, we're then talking about kilowatts. And kilowatt hours is simply the kilowatts multiplied by the hours. So 94 watts divided by 1000, and then we multiply by 1250 hours per year, and that gives us 117.5 kilowatt hours, or another way to put it, 117.5 units of electricity. Now let's just do the same for the others. So we saw that our 6 millimeter cable there, that was actually 63 watts, and again we're going to divide that by 1000, so we get kilowatts, multiply by 1250 hours, which gives us our total kilowatt hours. And again, same with the 10 millimeter square cable, that was a 37 watt dissipation in the cable, divide by 1000 for kilowatts, multiply by 1250 hours, gives us the total kilowatt hours or units of power there. So the wastage in the cable then is going to be 117, 78 or 46, depending on what size of cable we use. Now how much does this actually cost in real terms? Well, of course it depends on how much you pay for electricity. What we'll assume here is sort of an ordinary sort of figure in the region of 15 pence, or basically I'll put 1.5. Of course some areas may be less than that, some areas may be considerably more. It will depend on who you're buying it from and where you live and various other factors. And then to get the cost of this per year, all we need to do is multiply these by our 15 pence per unit. So our costs per year are, say, basically just this kilowatt hours multiplied by 15 pence. For the 4 millimeter cable, £17.62 per year, just in the waste in the cable itself. For the 6 millimeter, £11.81, and for the 10 millimeter, £6.94. And bearing in mind this is purely the waste from the cable which is given off as heat over the course of 1 year. And again, bearing in mind we've chosen this here because it is going to be on for a long time, 1250 hours a year, which is say 5 hours a day, 5 days a week. You can do this with other things, but of course if it's only on for a short time at a low load, these figures will come out in the pence kind of range. Now all of these are electrically compliant, there's no particular problem there, but what we're trying to consider here is whether it's worthwhile paying initially for a bigger size of cable, because it might save the homeowner or whatever some money in the longer term. So £17.60, £11.80 and £6.94. So roughly the difference between these is about £6 a year between those two. And between these two it's approximately £5 difference as well. So then the question is saving £6 a year worth it when initially you're going to have to pay more for some 6 millimeter squared cable compared to 4 millimeter squared? Again, this is a 10 meter long piece we're talking about. And again, is it also worth paying even more for the cable initially to save, say, an extra £5 compared to the 6 millimeter, or basically about £11 if you go straight from the 4 up to the 10? Now, how much does this cable cost? Well, 10 metres, we're going to assume it's steel wire armoured. We're also going to assume it's 3 core because that's pretty much the usual choice there. Now, just had a quick look at an online supplier because it's just easier to get a set of comparable prices. Obviously, your suppliers may be different, whatever. But for the 3 cable types, we've got a price of the 4 millimetre, £2.34 per metre, which will make it £23.40 for the piece of cable 10 metres long. 6 millimetre cable of the same type is going to be £31.10, and 10 millimetre comes out to £5.15 a metre, so that will be £51.50. So the difference between these, so if you went from 4 to 6mm, that's actually £7.70 more expensive for the installation. Bearing in mind everything else is going to be the same because it's the same equipment, it's the same fixings to the wall, same labour, whatever else. It's just a bit bigger wire. So £7.70 more, but on the other hand, assuming you use it for those amounts of time, it's going to save you £6 a year in electricity costs due to the reduced wastage in the cable. So that might be worth considering, because after, what, about 14 months or something, you've actually covered the cost of the extra cable, or the extra size cable, and then you're actually saving money. Now if you go from this one to this one, that's actually going to cost you £20.40 more if you go from 6 to 10, to save at £5. So maybe not quite as worth it. So spend £20 extra to start with, save an extra £5 a year. So that's going to be about 4 years before you recover the costs you initially paid. But on the other hand, are you going to keep your car charger for more than 4 years? Well, quite likely. Generally, it's a fairly long-term thing you're going to have put there. So after year 4, again, you're saving about £5 a year extra. So again, might be worth considering. And again, it all depends on how long you're going to use it for. Say we use the 1250 hours a year there, but obviously different people will use things differently. And then the other thing is, does this have any kind of implication in the regulations here? And the answer is possibly. Now, when the draft copy of this came out, there was actually going to be a section 8 which did cover energy efficiency. That was actually not put into this final version. However, there is an appendix 17 here which is titled energy efficiency, and being hidden at the back, it's something that a lot of people may not have even looked at. And if you have a look down inside here, we can see what it has here about voltage drop. Consideration should be given to limiting the voltage drop within installation to a level below that required by regulation 525202, which is the one about the 3 and 5%, to reduce the energy losses in the wiring system. So that's exactly what we've been looking at here. How much energy is wasted in just the cables themselves, and is installing bigger cables for a fairly small extra cost worthwhile in terms of savings financially, and also for not wasting energy and destroying the environment. Now that is it for this particular video, and until next time, thanks for watching.